When concurrent processes within a computer system collide over limited hardware, the entire operating system grinds to a complete stop. This diagram shows the mechanical definition of a deadlock, a state where processes are permanently blocked, waiting for resources held by another. P1 cannot finish without R2, and P2 cannot finish without R1. The system is trapped in an inescapable cycle of dependency. For this exact state to exist, 4 specific conditions must occur simultaneously. 1. Mutual exclusion. 2. Hold and wait. 3. No preemption. And 4. Circular wait. Because deadlock states force manual reboots and severely degrade performance, operating systems require strict engineering protocols to stop them from forming in the first place. However, solving the deadlock problem creates a conflict with performance. Eliminating the possibility of a freeze is mechanically straightforward, but the stricter the rules, the more the system's throughput and speed suffer. This split-screen flowchart illustrates the 2 primary architectures engineers use to solve the problem: deadlock prevention and deadlock avoidance. Prevention relies on static, structural rules to restrict exactly how system resources are requested and allocated. Avoidance takes a completely different path. It relies on predictive mathematical analysis at runtime to navigate around dangerous system states. Navigating these states requires a choice between implementing structural restrictions that guarantee safety or using runtime analysis to maintain higher concurrency. The logic behind deadlock prevention is entirely subtractive. Since all 4 conditions are mathematically required for a deadlock to form, breaking just one of them guarantees the system remains safe. Software engineers can target the first condition, mutual exclusion, by configuring resources to be simultaneously shareable. If multiple processes can read a file at the exact same time, they don't have to wait on each other. The immediate limitation here is hardware physics. A printer or a physical I/O device cannot safely process overlapping data streams from multiple sources at once. Mutual exclusion is often unavoidable, so architects move to the second condition, hold and wait. They break this by forcing a process to request every single resource it will ever need entirely up front, before any execution begins. This timeline models the resulting inefficiency. Because resources are allocated at once, they sit entirely locked and unused. A process might spend 90% of its lifecycle completing memory-intensive calculations, hoarding a locked printer it won't command until the final second. To fix that waste of hardware, an operating system could attack the third condition, no preemption. Under this rule, if a process requests a new resource and is denied, the OS violently strips away all the resources that process currently holds. The process breaks its hold, satisfying the prevention logic. But aggressively terminating and restarting tasks is highly disruptive, particularly for complex data operations that cannot be safely rolled back. Breaking any of these first 3 conditions achieves absolute mathematical safety, but it does so by introducing operational bottlenecks and forcing expensive hardware to sit idle. That leaves only one practical target for a strict prevention architecture: breaking the 4th condition, the circular wait. This diagram maps out how it works. The operating system assigns a strict numerical ordering to every resource type. Processes are only permitted to request resources in increasing numerical order. If a process holds resource number 3, trying to request a lower order resource, like number 1, violates the architecture. The request is immediately rejected. By forcing resource acquisition to flow in one irreversible direction, forming a circular dependency graph becomes mathematically impossible. It is an incredibly effective safeguard, yet it still forces developers to write applications that conform to an arbitrary, rigid hierarchy rather than the logical flow of the software. Summing up the strategy of deadlock prevention reveals clear operational costs: idle hardware, reduced efficiency, and longer process wait times. Static prevention solves the deadlock problem by essentially suffocating the system's ability to multitask. To maintain high concurrency, software engineers needed a solution that allowed for flexibility. This is exactly where the architecture shifts from rigid structural rules to intelligent predictive foresight. Deadlock avoidance leaves all 4 conditions intact. It allows mutual exclusion, holding, and circular requests. Instead of banning behaviors, it subjects every single resource request to a rigorous preemptive analysis. The foundational metric driving this analysis is called the safe state. A safe state exists when the operating system can calculate at least one guaranteed sequence of execution that allows all active processes to secure their resources and successfully finish. Conversely, an unsafe state occurs when the system looks at the available hardware and can no longer explicitly guarantee a successful execution sequence for everything currently running. Entering an unsafe state does not mean the system is deadlocked. It simply means the mathematical probability of a deadlock forming in the future is now greater than 0. To steer systems entirely clear of these unsafe states, operating systems rely on a mechanism proposed by computer scientist Edsger Dijkstra, known as the banker's algorithm. This matrix grid represents how the algorithm works. Whenever a process requests a resource, the OS doesn't hand it over immediately. It temporarily assumes the request is granted within an isolated sandbox environment. The algorithm projects the future state matrix to verify if a safe sequence still exists. If the projection holds and the resulting state remains safe, the OS officially executes the transaction and grants the hardware. But if the projection fails and uncovers an unsafe state, the OS actively protects the system. It explicitly denies or delays the request until more resources free up elsewhere. By substituting restrictive physical rules with predictive computational simulation, Deadlock Avoidance actively dodges system-killing freezes before they ever physically manifest. Evaluating these two architectures head-to-head comes down to measuring the cost of rule-based restriction against the cost of state-based prediction. This comparison matrix lays out the exact differences in how the two approaches allocate system power. Prevention requires very little system information to run, but strictly limits allocation. Avoidance, on the other hand, enables flexible, high-efficiency allocation, but requires continuous, demanding system data to function. That continuous data is the hidden cost of avoidance. Projecting state spaces thousands of times a second creates immense computational overhead. The algorithm also requires advanced knowledge of the absolute maximum resources every application might request, which isn't always possible. Because of these extreme demands, general-purpose modern operating systems rarely implement strict deadlock prevention across their entire architecture. In highly dynamic, unpredictable user environments, the daily performance degradation caused by rigid prevention rules is mathematically worse than simply suffering a rare deadlock and forcing a recovery. Instead, standard operating systems deploy localized locking rules and intelligent allocation routines to manage everyday processes. Strict avoidance strategies are reserved for specialized, high-stakes environments where a crash is unacceptable. Enterprise databases and transaction managers run rigorous banker's algorithm-style checks, because when millions of financial records are moving concurrently, data corruption is not an option. Absolute safety always comes at a sacrifice in raw efficiency, but by utilizing predictive algorithms to map the system's state space, engineers can push operational concurrency to its maximum limit without crossing the line into a catastrophic freeze.